Hello everyone, welcome back to Math 251. This is section 4.2. Today's mathematician of the day is Pedro Nunes, who was a 16th century Portuguese mathematician who made contributions to nautical navigation and map-making during a time when Portugal was discovering new trade paths. Pretty awesome. And did you know that the elements of geometry as we know it were published by a guy named Euclid in the 4th century BC? We still use his work every day. This stuff has been around for a long time. Today we will be discussing something called the mean value theorem. If you remember, last time we talked about absolute and local extrema, and I mentioned that we were going to be talking a lot about graphs. So this is another graph section. The mean value theorem is all about graphs. But before we get to the mean value theorem, we have something else called Rolle's theorem. And Rolle's theorem says this: let f be continuous on a closed interval from a to b and differentiable on a and b, a to b, with f of a is equal to f of b. This is pretty important. We need our two endpoints to have the same y value. Then there is at least one point that we call c in our interval such that f prime of c is equal to 0. So what does this look like? Well, if I have a function here, let's call this a and this b. As long as I have that f of a is equal to f of b, so this is f of a and f of b, well then my function, as long as it's differentiable and continuous, will have to go up and then come down at some point. So at this local max, that is where f prime of this point c is equal to 0. So that is what this looks like. So why does this theorem require differentiability and continuity? Well, I could have a function that looks like this, say. So f of a is equal to f of b here, right? They're both equal to 0. However, this is not continuous. And in this particular example, we don't have a point c such that f prime of c is equal to 0. I have non-horizontal tangent lines at every single point in this interval from a to b. So that's why we require continuity. What about differentiability? Say I have something like a, b, something like this. Well, I still have here that f of a is equal to f of b, but I'm not differentiable at this point right here. And again, on this particular graph, there is nowhere that I have a horizontal tangent line or where my derivative is equal to 0. So that's why we require differentiability and continuity. The reason that we need f of a to equal f of b is because that guarantees that if we go up, we will come back down and we'll have a local max, or if we go down, we have to come back up and then we'll have a local min. So let's do an example using Rolle's theorem. Find an interval on which Rolle's theorem applies to the function x cubed minus 7x squared plus 10x. Then find all points c in this interval such that f prime of c is equal to 0. So the first thing I need to do is I need to find 2 points a and b such that f of a is equal to f of b. A and b such that f of a is equal to f of b. Now I can choose whatever value I want here. I can choose f of a to be equal anything, and as long as f of b is the same as that value, then we're fine. So I could, set them both equal to 100 or negative 2000, but really the easiest thing for me to do here is to make them both equal to 0. Again, you could choose any number here, but setting it equal to 0 makes it a little bit easier for us. So let's find where I have 2 points such that my function f is equal to 0 at these 2 points. So my f of x equals x cubed minus 7x squared plus 10x. From each of these terms, I can factor out an x, and I'm left with x squared minus 7x plus 10. And this factors as x times x minus 5 times x minus 2. So that means that f of x equals 0 at setting each of these terms equal to 0. I get that f of x equals 0 at x equals 0, x equals positive 5, and x is equal to 2. So I can use any combination of these 3 points that I want. I could say my interval, I could say a is equal to 0, b is equal to 2. I could say a is equal to 2, b is equal to 5. Or I could say a is equal to 0, b is equal to 5. So I could choose any two numbers here. I'm going to choose 0 to 5. So I'm going to set a equal to 0, b equal to 5. So this guarantees that f of a is equal to f of b. That is one thing that Rolle's theorem requires. The other is that f is continuous and differentiable. Well, we are dealing with a polynomial, so I know that f is continuous and differentiable everywhere. So I don't need to worry about that in this example. Okay, so I want to find a c value between my 2 points 0 and 5 such that f prime of c is equal to 0. So I want f prime of c equals 0, and I'm trying to find this point c. So I see that f prime of x, taking the derivative, is equal to 3x squared minus 14x plus 10. And I want this to equal 0. Well, I'm going to have to use the quadratic formula here. Since it doesn't really factor easily. And when I use the quadratic formula, I get x is equal to 14 plus or minus the square root of 196 minus 4 times 3 times 10 over 6. And if we do the math, this is approximately 0.88 and 3.79. So in this case, I have 2 points c in my interval from 0 to 5 such that f prime of c is equal to 0. If I had chosen my interval to be from 0 to 2, then I would just have one answer. It would be that 0.88. If I had chosen from 2 to 5, then I would just have that one answer of 3.79. But since I chose my interval to be from 0 to 5, I have 2 c values such that f prime of c is equal to 0. So these are my c values. Alright, let's try another example. We want to find an interval on which Rolle's theorem applies to the function f of x is equal to sine of 2x, then I'll find all points c on this interval such that f prime of c is equal to 0. Alright, so I want, first of all, I need to find 2 points a and b such that f of those points a and b are equal to each other. And again, I think it's easiest to find our y value of 0. So I know that sine of x, plain old sine of x, is equal to 0 when x equals 0, when x equals pi, and when x is equal to 2 pi. So sine of x equals 0 when x equals 0, pi, and 2 pi. What does that say about sine of 2x? Sine of 2x equals 0. Well, since I'm multiplying my x value by 2, I need to divide all of these by 2 to kind of cancel out that multiplication by 2. So sine of 2x equals 0 when, well, 0 divided by 2 is 0. Here this will be pi over 2, and this will give me x equals pi. So I have 3 possible points here, and again I can choose any combination of them for a and b, but I'm going to choose 0 to pi over 2. So choose a equals 0, b equals pi over 2, and this means that f of a is equal to f of b, and I chose them both to equal 0. So that condition is satisfied here. My function sine of 2x is differentiable and continuous everywhere, so that is good as well. So now I want to find a c on the interval from 0 to pi over 2, such that f prime of c is equal to 0. So I need to find f prime first. So f prime of x, using the chain rule here, I get that this is 2 times cosine of 2x. And I want this to be equal to 0. So if I divide both sides by 2, I get cosine of 2x equals 0. And let's see, I know that cosine of x, plain old x, is equal to 0 when x equals pi over 2 and 3 pi over 2. So that means that cosine of 2x equals 0. Again, I divide both of these x values by 2 in order to compensate for the multiplying by 2. So when x is equal to pi over 4 and 3 pi over 4. So I have these two possibilities right here, x equals pi over 4 and 3 pi over 4 for my c value. In this case, only one of them is in my interval from 0 to pi over 2. So I get that f prime of pi over 4 is equal to 0. Pi over 4 is in my interval from 0 to pi over 2. If I had chosen the interval from 0 to pi, then I would have both of these answers, and so on. So this pi over 4 here is my c value. This is the value guaranteed by Rolle's theorem, such that my derivative is equal to 0 at this point. Alright, so Rolle's theorem is kind of like a toddler or baby version of the mean value theorem. So this kind of warms us up to the idea of the mean value theorem, which we are going to learn now. So this is the mean value theorem. If f is continuous on the closed interval from a to b and differentiable on a to b, that should look familiar, then there is at least one point in the interval from a to b such that the following is true. F of b minus f of a over b minus a is equal to f prime of c. So in the previous Rolle's theorem, right, we had all of the same conditions, except we had f prime of c is equal to 0. Here we have f prime of c is equal to f of b minus f of a over b minus a. So let's look at that a little bit closer. F of b minus f of a over b minus a should also look familiar. This is simply the slope between the points a and b. So what the mean value theorem says is that there is a point c such that the slope at c is the same as the slope between a and b. Another way to think about the slope between a and b, as we learned, this is the secant line between a and b. So there's some point c in this interval such that the slope of the secant line between a and b is equal to the slope of this point c. So let's draw a picture here and see what exactly is going on. So I have a function that's going to look something like this, and whoops, sorry about that. And in this case, I don't need f of a to equal f of b. So say my function looks like this, and we'll call this point right here a, and we'll call this point right here b. They don't need to have the same y value in this case. So if I were to draw the secant line between a and b, it would look like this. So this is the secant line. And this is also, the secant line has the slope f of b minus f of a over b minus a. So that is the slope of the secant line. And what the mean value theorem says is that I can find a value c in between a and b such that the slope of f at c is the same as the slope of the secant line. So basically I'm trying to find a parallel line such that the tangent line at c has the same slope as this secant line between a and b. So it looks like it's about here. If I were to draw the tangent line here, actually a little bit further. If I draw the tangent line here, then this tangent line has the same slope as this secant line. So these two lines are parallel to each other. So this is the tangent line at C. If I draw C here, this is C. X equals C. And it has slope f prime of C. So our mean value theorem guarantees that there is a point C here such that the slope of the tangent line at that point is the same as the slope of the secant line between A and B. So let's write that down. There is a point C such that the secant line at C, between A and B and the tangent line at C have the same slope. This is a very useful theorem, as we will learn, but this is what it looks like pictorially. All right, let's do some examples using the mean value theorem. Let's determine whether the interval f of x, the function f of x equals x times natural log of x satisfies the conditions for the mean value theorem on the interval from 1 to 2, and if so, we want to find that c value. So this function, x times natural log of x, is continuous and differentiable on the intervals from 1 to 2. I can't take the natural log of a negative number, so that's what I have to worry about here, but our interval does not contain any negative numbers, so I see that f is continuous and differentiable on 1 to 2. So we can use the mean value theorem. This function is not continuous and differentiable everywhere, but it is on this interval. So I want to find a point C. Oh gosh, so sorry. Find a point C such that our interval is 1 to 2. So I want to find a point C such that f of 2 minus f of 1 over 2 minus 1 is equal to f prime of C. That is what the mean value theorem states. My b value is 2, my a value is 1. So this is what we're looking for. So I first need to figure out what this left-hand side is. So let's find f of 2 and f of 1. So f of 2 is equal to 2 times the natural log of 2. Okay, and f of 1 is equal to 1 times the natural log of 1. Well, the natural log of 1 is equal to 0, so this just equals 0. So this gives me that f of 2 minus f of 1 over 2 minus 1 is equal to, our denominator simplifies as just 1, so this is 2 times natural log of 2. And again, I want this to be equal to f prime of c. I'm trying to find that c value. So next I need to find the derivative of my function and find a point where that derivative is equal to 2 times natural log of 2. So using the product rule on our f of x equals x times natural log of x, I get f prime of x is equal to the first times the derivative of the second plus the second times the derivative of the first. This simplifies as 1 plus natural log of x. So this is my f prime of x. And I want this somewhere to be equal to 2 times natural log of 2. And I want to find where that somewhere is. So I set 1 plus natural log of x, that's f prime of x, equal to 2 times natural log of 2. And I'm trying to solve for x here. So let's see, if I subtract 1 from both sides, oh sorry, I can't subtract 1. Well, yeah, I can. Okay, that's fine. So I get natural log of x is equal to 2 natural log of 2 minus 1. Now to solve for x, I need to raise each side, e to each side as a power. But before I do that, I can employ some natural log rules and bring this 2 as a power of this 2 right here. So this will give me natural log of x is equal to natural log of 2 to the power of 2 is equal to 4 minus 1. So now to solve for x, I raise e to this side, e to this side. This gives me x is equal to e to the natural log of 4 is just equal to 4 minus e. So the x value such that f prime of x is equal to 2 times natural log of 2 is 4 minus e. Ooh, that's a lot of work, huh? All right, let's do another example. We would like to determine whether the function f of x equals 2x cubed minus 3x plus 1 satisfies the conditions for the mean value theorem on the interval -2 to 2. If so, find the points guaranteed by the MVT. Well, in this case we have a polynomial, so it's pretty obvious that it's continuous and differentiable everywhere, so we don't have to worry about that. Okay, so I want to find a point C such that f of 2 minus f of -2 over 2 minus -2 is equal to f prime of c. This is what the mean value theorem says. So I need to find f of 2 and f of -2. F of 2 is equal to 2 times 2 cubed minus 3 times 2 plus 1, which is equal to 11. And f of -2 is equal to 2 times negative 2 cubed minus 3 times negative 2 plus 1, which is equal to negative 9. So this becomes f of 2 is 11 minus negative 9 over 4. This simplifies to 20 over 4, or 5. And I'm looking for a c value such that my slope of f at that c value is equal to 5. So I want f prime of c to be equal to 5. So if I take f prime of x here, I get f prime of x is equal to 6x squared minus 3. And I want this to equal 5. So if I add 3 to both sides, I get 6x squared equals 8. Dividing both sides by 6 gives me x squared equals 8 over 6, or 4 over 3. So taking the square root of both sides gives me x is equal to plus or minus. Remember, when I take a square root, I have to do a plus and a minus. Square root of 4 over 3, also known as plus or minus 2 over square root of 3. Both of these, the plus and the minus, happen to be in my interval from negative 2 to 2. So in this case, I have two c values such that the slope of f at those two c values is the same as the slope of the secant line between negative 2 and 2. And of course here, the slope of the tangent line here is 5. This 5 right here. All right, I think these problems are pretty fun. I don't know about you guys. Next we have a word problem, which may seem a little bit strange, but there are a lot of applications to the mean value theorem. So our example says, your dog is a super runner and often runs 10K races without you. Her best time is 30 minutes, and at the end of the race, she was so excited to see you that she stopped right at the finish line for some noggin pats. Show that at least once during the race, her instantaneous speed was 20 kilometers per hour. So this instantaneous speed, what does this mean in terms of a graph? Instantaneous speed represents the tangent line on a graph. We also had that she runs 10K in 30 minutes. So her average speed is, average speed, well, if I multiply that 30 by 2, I get 1 hour. So her average speed, if she runs 10 kilometers in 30 minutes, she'll run 20 kilometers in an hour. So her average speed is 20 kilometers per hour. So this dog runs continuously, right? She doesn't I don't know, vanish at some point, and her path, that means, is differentiable. So she runs continuously and differentiably. Continuously and differentiably. I don't know if differentiably is a word, but I just made it a word. So our mean value theorem applies here. So by the mean value theorem, at some point, her instantaneous speed, or the tangent line on the graph, is equal to her average speed, which is 20 kilometers per hour. At some point, her average speed, remember average speed is like the secant line, will equal her instantaneous speed. So at least once she's running 20 kilometers per hour. And this makes sense intuitively, right? If you drive an average of 60 miles per hour, right, for an hour, at some point you will be going exactly 60 miles per hour. It doesn't matter if you travel consistently at 60 miles per hour, no stopping, no slowing down. If you go 55 for a while and then 65 for a while, at some point your instantaneous speed will be exactly 60 miles per hour, if that is your average. So intuitively, hopefully this makes sense. All right, we end this section with a super random theorem, and I don't know why the textbook threw it here. I wouldn't worry so much about this, but I do need to say it. So our theorem here is zero derivative implies constant function. If f is differentiable and f prime of x is equal to 0 at all points in an open interval, then f is a constant function on that interval. This makes sense, right? If my derivative is 0, I just have a horizontal or constant function. And the other theorem we have is functions with equal derivatives differ by a constant. So if two functions have the property that f prime of x equals g prime of x for all x in an interval, then the only thing that's different about them is that they are different by a constant, or just, raised up or down a little bit. So if, for example, I have f of x equals x and g of x equals x plus 3, obviously these two graphs have the same derivative, right? Both of these derivatives are equal to 1. The only thing that's different about f and g is that it differs by a constant. So if I were to draw these on a graph, right, I would have f of x like this. I would have g of x like this. They are parallel, so they have the same derivative, but the only thing that's different about them is they differ by a constant, in this case 3. Kind of random, but yeah, the bulk of this section is about the mean value theorem and a little bit about the Rolle's theorem. Hopefully this makes sense to you. If not, I'd love to see you during our Zoom meeting today. Other than that, have a great weekend, and I'll see you on Monday.